Hello and greetings to everyone. I'm covering WebWork number 9, Problem 23 on gradients and directional derivatives. Let's take a closer look. Here we have a function of two variables, 3x squared plus 2xy plus 3y squared, a point 0, -3, and a direction vector of 8 over 10i plus 6 over 10j. Part A asks us to find the gradient of the function. The gradient gives us a vector that points in the direction of maximum increase of the function at a point. For a function of two variables, it is composed of the partial derivative with respect to x in the I direction and the partial derivative with respect to y in the j direction. We'll begin by finding the partial derivatives. The partial with respect to x is 6x plus 2y, and the partial with respect to y is 6y plus 2x. This gives us the gradient for any point on the surface of our function. What's important to remember is that the actual vector we end up with may differ depending on the point we use. Imagine standing on a hillside. The direction where the hill climbs the steepest will vary depending on where we are standing. It's also important to remember that the direction of steepest ascent does not necessarily mean we are heading towards the highest point on the hill or the absolute maximum value of a function. Question B asks us to find the directional derivative of f in the direction of the vector u. Directional derivatives give us a value. This value tells us the slope of the surface in any direction indicated by the unit vector given to us. Just like there are many direction vectors for a point, there are also many directional derivatives for a point. One directional derivative for every unit direction vector. Our direction vector here is 8 over 10i plus 6 over 10j. Let's begin by verifying that this is in fact a unit vector. Taking the square root of the sum of the squares of the vector u yields a 1, so it is in fact a unit vector. If it were not a unit vector, we would need to normalize it before proceeding. The directional derivative takes the partial of the function with respect to x, multiplied by the I component of the unit vector, and adds it to the partial of the function with respect to y, multiplied by the j component of the unit vector. Since the partial with respect to x is 6x plus 2y, as we found in Part A, and the partial with respect to y is 6y plus 2x, the directional derivative of f in the direction of the vector u is 6x plus 2y multiplied by 8 over 10 plus 6y plus 2x multiplied by 6 over 10. Like the gradient we found, this is a general equation for our function in a particular direction. The exact value of the slope will vary based on the point on the surface we select. This leads us to questions C and D, which asks us to evaluate and compute the gradients and directional derivatives at the point 0, -3. The gradient at point 0, -3 in the I direction is 6 multiplied by 0 plus 2 multiplied by -3 equals -6. And in the j direction, 6 multiplied by -3 plus 2 multiplied by 0 is -18. This gives us a gradient vector at the point 0, -3 of the function at -6i minus 18j. For question D, we take our directional derivative and evaluate it at the point 0, -3. Notice that this is a dot product between the gradient and the unit vector. The gradient value, as we found in question C, is -6 for the I component and -18 for the J component. So we multiply -6 by the value of the unit vector of the I component, 8/10. Subtract that from 18 multiplied by 6/10, and we end up with a directional derivative of the function at the point 0, -3, equaling -15.6. This tells us that the slope of the surface is decreasing when we are in the direction of the unit vector. We have now covered all of problem 23. I hope this has helped define the important information we can derive from finding a gradient and a directional derivative of a function at a point. Thank you.